So this is problem 27.47 and it deals with RC circuits. So now these are the equations that we're going to be using. We're going to use a loop rule. We're also going to use the discharging equations for an RC circuit. So this is the current and this is the charge. We're also going to use these two equations here. Now, A says, find the steady state current in each resistor when we have this switch here is closed. So this is our circuit now, and we've waited a really long time, and this capacitor is fully charged. So we want to know what is I through these resistors. This is I1, I2, and I3. Now, straight off the bat, we know that I3 is equal to 0. The reason why we know that is because this is fully charged, and when it's fully charged, it means no more current is flowing here. There is still current flowing around this path. Now we can also notice that this path, here our resistors are in series. And when they're in series, for one, we know that they all have the same current going through them. So I1 is equal to I2. And we also know that our equivalent is equal to R1 plus R2. So what we're going to do is reduce this down to an equivalent resistor. And we're doing this so that we're able to calculate what is the current through this resistor, which is going to be the same as it is through I1 and I2. So now we know that this is 9 volts, and we have our equation from above right here. So we know that I is equal to E, because here we're talking about this here. So we're told that there's no resistance inside. So we're given the potential difference across the battery. So it's going to be E divided by R equivalent, right? And that's just from this equation here. So that is going to be 9 volts divided by R1 plus R2. We have 15 plus 12 is going to be 27 kilo ohms. And that is going to give us an answer of 333 microamps. So what we've just found is that in the steady state, I1 is equal to I2 is equal to 333 microamps, and I3 is equal to 0. So that's it for A. Now B says, find the charge Qmax on the capacitor. Now the idea is that we know it's fully charged, but well, how much charge is actually on it? Normally what we would do for this is reduce this down all to a singular situation like this, where we maybe only have one capacitor, one resistor, but the problem is we can't do that because we have these two loops. So what we're going to do is actually use Kirchhoff's loop rules. So we're going to start here, B, and we're going to look at our loops. Number 1 is this one. And we are going to see where are the potential gains and potential drops. So here we have a gain and potential, drop, drop, and drop. So E is equal to I1, because remember this is 1, 2, 3. I1, R1. I should say that we can also write this as E minus I1, R1 minus Q over C, that's the drop across the capacitor, minus I3, R3, but remember I3, R3 is 0 in the steady state solution, and this is equal to 0. Our second loop in black is this smaller one, and we're going to have E minus I1, R1 minus I2, R2. Now remember what it is we're trying to figure out. We're trying to figure out what is Qmax. And we know that Qmax occurs when this is true. So whenever I3 is equal to 0, we're at our Qmax. So this here is Qmax. So let's just solve for Q here. We have Q over C is equal to E minus I1, R1. And we see here that we also have E minus I1, R1 on this side. So then we just solve for that. We see that E1, so E minus I1, R1 is equal to I2, R2. Plug that in here and we get Q over C is equal to I2, R2, or Q is equal to C, I2, R2. From here, that's pretty easy to solve, right? So this is equal to, what is the capacitance? We just go back up here. We have 10 microfarads. We already calculated I2, 333. And R2 is just going to be 15 kilo ohms. Multiply everything together, and Q max is equal to 50 microcoulombs. Now moving on to C. C says, the switch is now opened at t is equal to 0. Write an equation for the current in R2 as a function of time. So what happens to the current in R2? Well, if we close this, this switch here, what we're going to have is current discharging. So we're going to have discharge from this capacitor going in this loop here. Now, basically, this is going to be inaccessible. This is inaccessible. The only thing that's happening is a discharge process through R3 and R2. Now, we want to figure out what is the current through R2. The first thing we're going to note is that these two resistors are now in series with one another, so we can deal with those like we know how to. And we also know that this is the equation that we are looking for. We're looking for the current, and we know that for an RC circuit like we have here, we need to find tau, which is just R times C, and we need to find I initial. So what is the initial current throughout the system? Because the current's going to be the same everywhere, but it's going to be reducing in time. So we need to figure out those two things. So this is C. We're essentially going to reduce our system down to an equivalent resistor and a capacitor. Because remember, whenever we have our resistors in series like this, the current going through this one is the same as the current going through this one, and it's the same as the current going through our equivalent. So let's figure out what tau is. Tau is R times C, but here, of course, we have R equivalent. So that's going to be 15 kilo ohm plus 3 kilo ohm times 10 microfarads, and that is 0.18 seconds. So this is tau. We also need to figure out what our initial current is through our equivalent. Now we know that it's going to be equal to delta V divided by R equivalent. Now what is delta V? We know that here we're going to figure out what is the potential difference across here, our capacitor. So I should write that out here, delta VC, and that potential difference is going to be the same potential difference across the resistor here. So at the initial point in time, when the switch is immediately flipped, we have a certain potential difference here, and it's going to be the same as the potential difference here. So what is it? Well, it's going to be equal to I2, R2, because remember, we already had current going through this resistor at the beginning, right? There's already some current here, and so we know that at that immediate point in time, when t is equal to 0, we have this initial current going through here. Now what it is, I2 times R2. So then this is divided by R equivalent. And so this here is going to be equal to, we already found that, 333 microamps times 15 kilo ohms divided by R equivalent, which we know is 15 kilo ohms plus 3 kilo ohms. And that is going to give us 278 microamps, which might seem a little bit weird because you'd think, well, there was a current originally, right? Like back in this problem, we had a current going through here, and that was I2. Like we had this current, and then all of a sudden it drops, right? And it's because we're looking at what happens when immediately, right after we flip the switch, instead we're only going to be having our current go around here, and there's going to be an immediate drop, well, because this starts discharging. So then here we have tau, and we know I initial. So then we just pull out our equation here, right, which is this. And then we just need to solve for I. So we got I, the current going through R2 at any moment in time, is equal to negative 278 microamps, e to the negative t divided by 0.18 seconds. And that is what we have here. Now we can draw this out. And remember, this is valid for t is bigger than 0. So if we draw it, we have this time current across R2. Before we flip the switch, we had a constant 333 microamps. As soon as we remove that battery from the circuit here, so now we don't have any more battery, so now the current is only flowing around this way here, we have an immediate drop in our current like this, and it drops to 278 microamps. That's how much current we have. Now, as time progresses, so this is t is equal to 0, we have a drop off like this, where as t goes to infinity, current goes to 0. So it fully discharges at some point, and this is kind of the situation we have. Now we have one more part to this problem, and it is this. It says, find the time interval required for the charge in the capacitor to fall to 1/5 of its initial value. We already know what this is here. So this is Q. This is the charge on the capacitor. And we know that it starts off at some Q initial, which is Q max, which we already figured out what that was. And then e to the negative t over tau. So let's just write that out here. We have for D, Q is equal to Q initial, e to the negative t over tau. And if we remember, we know that Qi, this is Q max. If we just go back, we already found that to be 50 microcoulombs. And we know that tau, and we already found that here, is equal to 0.18 seconds. And all we want to know now is to figure out, well, at what point did Q, little q, equal Qi divided by 5, so 1/5 of the original value. So Q initial over 5 is equal to Q initial, e to the negative t over tau. All we have to do from here is divide Q initial on both sides, and we get 1 over 5 is equal to e to the negative t over tau. And we know that if we take the natural logarithm on both sides, we get ln 1 over 5 is equal to negative t over tau. And all we have to do from this point on is say, okay, well, we know what tau is. Tau is equal to 0.18 seconds. So then here we have ln 1 over 5 times 0.18 seconds, negative sign here, is equal to time t. We plug in everything like that, and we get 290 milliseconds. So this is the amount of time it took to reduce the charge on the capacitor to 1/5 of its original value.